Hey guys, this is Mr. Mitchell. Today we're going to be talking about ionic bonds. So just a real quick review of ions. Previously we spoke about how ions form, and they happen because different elements will give away or accept extra electrons in order to get into the noble gas column. So for example, sulfur, right, in order for him to be stable and become like a noble gas, he's going to gain 2 extra electrons, go 1, 2, and then he ends up in this column. Whereas something like sodium, right, he wants to either gain 7 or just give up 1 to work his way back to look like neon. So we were able to predict the charge on an ion by saying, okay, it's going to be the least distance for him to get into the 8th column, so they'll either gain electrons or lose electrons to get there, and then therefore they have positive or negative charge depending on whether they gained or lost. So when we deal with multiple atoms and multiple ions, we have to think of this opposites attract rule. So whenever we have 2 objects that have opposite charges, when they come close to each other, they get attracted. They want to be near each other. So you see this example in a magnet, right? When you bring the north end and the south end close together, they kind of snap together. The same thing happens with positive and negative charges. All right, so since those are attracted to each other, that's what's going to be kind of the foundation for our ionic bond that we call. So ionic bonds actually form when those electrons are transferred from one atom to another. So our example with sodium and chlorine. Sodium was in the first column on the periodic table, and so he wanted to, in order to get to the noble gases, he could either gain 7 or lose 1. So it's easier for him to lose 1, he gives it away. So he gives that electron away. Well, chlorine is on the 7th column, and so he wants to either gain 1 or lose 7. Well, he'll gladly accept that electron from sodium, and that's the basis for our ionic bond. So the electrons aren't just going off into nowhere, they're being transferred to other elements or other atoms. So when those electrons are transferred from sodium to chlorine, we end up with opposite charges. When sodium loses an electron, he gets a positive 1 charge, a +1 charge. And when chlorine gets an extra electron, he gets a -1 charge. So now I have these 2 oppositely charged particles sitting next to each other, and they are attracted to one another, and they form this ionic bond. So when we're going to predict which elements will bond together, it's not just like I throw whatever elements I want together and it works. There's specific ones that'll work together. So if we think about the way that we are able to predict the charges, remember that we have this staircase here, and it separates our metals from our nonmetals. So over on the left-hand side, I have my metals, and over on the right-hand side, I have my nonmetals. Well, if I think about kind of the charges to expect, remember we don't count the guys in the middle, the metals tend to be these guys over here. Well, lithium is a metal, right? And is he going to gain 7 to go into the noble gas category, or is he going to just give 1 up? He'll just give 1 up. So the atoms over here tend to lose electrons, which makes them end up with a positive charge. And the nonmetals, again, they're closer to the noble gases. They tend to gain extra electrons, and so when they do that, they tend to form negative charges. So the rule that we come up with for determining ionic bonds is that ionic bonds come from a metal and a nonmetal ion that come together. So we always predict, if I'm looking at a given compound's formula, I would say, oh, well, this has a metal and a nonmetal in it, that's an ionic bond, because we can predict those charges will be opposites. So ionic bonds form between metals and nonmetals. But it's not as simple as just putting together, the formula of the 2 things that are combined, because the electron numbers can vary, right? Sodium and chlorine worked out perfect because sodium wanted to give 1 electron away and chlorine wanted to accept 1 electron. But what about something that gives away 2 electrons, or something that wants to accept 3 electrons? Then things get a little bit more complicated. So the ratio is not always just 1 to 1. What we have to do is look at the charges of those ions to predict the chemical formulas. And you can think about it like the number of electrons needs to add up to those combinations of 8. So our example of magnesium and chlorine kind of sets us up with that. Magnesium is in the 2nd column, so he wants to take 2 of his electrons and give them away. So if I have magnesium, he tends to get a charge that's 2 positive because he gave away 2 electrons. That means he has 2 extra protons. And chlorine, well, he's in the 7th column. He just wants to gain 1 extra electron, so he tends to have an ion with a 1 minus. Well, if I put those two together, right, in a simple 1-to-1 ratio, I'd have magnesium with a 2 plus, and I'd have chlorine with a 1 minus, and I'd end up with something that had an overall charge. It would have like a 1 plus charge because these guys don't cancel out. So that doesn't work out. We cross that guy off. What we have to do is get it so that those charges balance out. Well, how am I going to do that? I have 2 positives but only 1 negative. Well, what happens if I get an extra chlorine with a negative sign? Well, now both of those together are 2 negative and they'll cancel out the 2 positive. So my formula for magnesium chloride is going to be MgCl2 because I need 2 chlorines to cancel out the charge of my 1 magnesium. We can do this with a bunch of different combinations, and so we're going to practice some of that. So we know how to predict the charges of ions using the periodic table. To predict the chemical formula on a compound, we just include enough of each ion to make sure the total charge is 0. So this is exactly what we just did. Here's another example, except this one has calcium. And so you see that calcium has the same 2 plus charge that our magnesium did. And so when we bring in chlorine, we need 2 of them to cancel out the 2 positive charge on calcium. So here's some practice. We'll just go through 3 of these really quick just to make sure that we get the hang of it. Okay, so what's the chemical formula for a compound formed between beryllium and bromine? Well, beryllium is over here on the left, right? It's in the 2nd column. That means he has 2 valence electrons, so he can either gain 6 to get to 8, or he can give up 2 to get to 8. So he'll give 2 away, and that means that my beryllium is going to have a 2 negative charge. So now we've taken care of that ion, we need to deal with bromine. Bromine's over here. He's in the 7th column, so he can either give 7 away or he can get an extra 1 to get into the noble gas column. Well, he's going to just pick 1 up, and that means that bromine's charge with an extra electron is going to be 1 negative. And I'm sorry, I messed up with beryllium here. It should be 2 positive. 2 positive. Because he gave 2 away, he's got extra protons. So this is obviously not going to cancel out in an even fashion because I have 2 pluses and 1 minus. So that means I'm going to need an extra bromine to cancel it out. These together would have a 2 minus to cancel out the 2 plus. And so my formula would be Be, just one of those, and then I have 2 bromines, so I do Br2. And that would be the formula for my compound from beryllium and bromine because we need the charges to cancel out. We'll go ahead and do another one, lithium and nitrogen. So lithium, he's in the 1st column right here. If he's in the 1st column, he can either gain 7 electrons to get over here, or he can just give 1 away. So he's going to give 1 away. It means lithium giving 1 electron away will have 1 extra positive. All right, so that's what his ion's charge would be. And nitrogen is in the 5th column, which means he has 5 valence electrons. He can gain 1, 2, 3, or he can give up 5. Gaining 3 is a lot easier, and so what he'll do is he will give those, he'll gain those extra 3. Nitrogen will have a 3 negative charge. Now, in order to cancel this out, I can't just add 1 more lithium because even if I have 2 of them, I still only cancel 2. I don't cancel all 3. So I'm going to need 3 lithiums to cancel everything out. And when I put that together, my formula would be Li3N. And that is the compound for lithium nitride. Last one, and then we'll be done with this. Potassium and iodine, so it's the same process, right? Potassium is in the 1st column. Is he going to gain 7 or give up 1? He'll give up 1. So potassium's ion will be a 1 positive because he gave up an extra electron. He's got an extra proton. Iodine is in the 7th column, so he can either gain 1 or give up 7. He'll gain 1 extra electron, so iodine has a 1 minus charge, and look at that. Those ones are convenient. The charges cancel out automatically, and so the chemical formula for potassium iodide would be Ki. No numbers needed here. So hopefully this was helpful. This is all we're going to take care of today. Once we know how to predict the charges of the ions, we can then use those charges to figure out exactly what compounds they can form and exactly how many of each ion I will need to form that compound and get an overall neutral compound.